Hey guys, so today we're going to talk about factoring, which is the opposite process of multiplying polynomials. There's lots of different techniques that we have to use to factor depending on what type of polynomial you're trying to factor and various other things that we'll look for. So we're going to start today with the first step that you would use to factor any polynomial, which is looking for a greatest common factor amongst all of the terms. Okay, so some of you guys actually may be able to do several of these steps without having to go through every single little step like I am. And that's eventually the goal, that you can do this all in your head. But today we're going to just start out step by step, kind of slow, and then hopefully we'll build up some efficiency as we move along. Okay, so in general, when we're trying to factor a greatest common factor out of a polynomial, what we want to do is look at the greatest common factor amongst all of the terms of the polynomial. So if I'm looking at 6n and I'm looking at 9, for example, okay? Now, finding a greatest common factor if one or more of the terms involves a variable is very similar to finding a greatest common factor through prime factorization of numbers. The idea is that we want to break each term down into the smallest of parts, and then all of the parts that each term shares is the greatest common factor. And here's what I mean by that. If we're looking at 6n, we can break that down into 2 times 3 times n. And we're looking at 9, we can break that down into 3 times 3. Okay, now if we're looking for a greatest common factor, that's the factor that they share. So between the 6 and the 9, they share 1, 3. And so that is the greatest common factor. Okay, so when we're factoring that out, we're going to put a 3 on the outside and then put in a set of brackets. And the set of brackets should be roughly the same size as the original polynomial, because inside, if you're factoring out a greatest common factor, you need the exact same number of terms. Okay, and the idea here is we want to think 3 times what equals 6n. Okay, well, 3 times 2n equals 6n. And then 3 times what equals 9? 3 times 3 equals 9. So that would be the second term. Another thing that you can do, and you'd want to sort of do this in a different color, or because this is rough work, is the first term is always the greatest common factor divided by the greatest, the original term rather, divided by the greatest common factor. And then the second term is the original term, the 9, divided by the greatest common factor. Okay, so 6n over 3 is 2n, and 3 over 3 is 9, or 9 over 3 rather is 3. Okay, here we're looking at 6c plus 4c squared. So again, some of you again by now may even be able to see what the greatest common factor is, but if not, just break everything down. So 6c is 2 times 3 times c, and 4c squared is 2 times 2 times c times c. Okay, so now if you're going through each little piece, they both have 1, 2, so I can underline that. They do not both have a 3, but they do both have a c. And so that is our greatest common factor. It's 2c. So I can pull that out, and then on the inside I must have 2 terms because that's what I started with. The first term is going to be the original divided by the GCF, 6c divided by 2c, which is 3. Or you can think of it as 2c times what equals 6c. And then the second term is going to be 4c squared divided by 2c. Well, 4 divided by 2 is 2. C squared divided by c is c. And that is fully factored. Okay, I'm going to let you guys try these two yourself, this 3g plus 6 and 8d plus 12d squared. The answers, though, and the full worked solution is in your completed notes. All right, now let's look at this next example. Really, the only difference between this example and the previous one is that we happen to have 3 terms instead of 2. Okay, and that happens very often. So all we're doing is looking for the greatest common factor amongst all of the terms. Right, so one thing that you can look for is that if one of the terms does not have a variable, the GCF will not include a variable. Okay, it can't because one of the terms doesn't have any variables in it. So here I see that there's like a constant of 5. there's not going to be an algebraic greatest common factor. There very well could be a numeric greatest common factor, but not an algebraic one because one of the terms is not multiplied by z. Okay, so now what you could do is instead of writing out each term split up into parts is just think, what's the greatest common factor between 5, 10, and 5? And the answer to that is 5. Okay, so we can take out a 5, and the first term is going to be 5 divided by 5, which is 1, or you think 5 times what equals 5. And then, so you could always do it this way as well. 5 divided by 5, that's a first term. The second term, 5 times what is 10z, that's 2z's. This is going to be minus 2z. Or you could think negative minus 10z over 5. And then the third term is 5 times what is 5z squared? Well, that's just z squared. So minus z squared. Or you could do it this way as well. Minus 5z squared divided by 5. Okay, and that should be factored. Now, how can you check, verify that the factors are correct? Do the opposite process, expand. If you get back to where you started, then you have probably factored correctly. Okay, so if I'm verifying, maybe I'll verify in a different color. Then I take the factored form, and I'm going to distribute the 5 into each term. So 5 times 1 is 5. 5 times negative 2z is minus 10z. And 5 times negative z squared, rather, is minus 5z squared. And so that's what we started with. So this is correct. Okay. Again, the check your understanding 2 is very, very similar to the last one that we did. So I'm going to skip ahead. Whoops, I got to go turn on the mouse. There we go. All right, so here we are looking at something that's slightly more complex because we've got 3 terms, we've got 2 variables, and there are a lot of different exponents on the variables. So when you're starting out, you may want to, again, look at quote unquote prime factorizing each of these terms. It's not really prime factorization because you can't prime factorize something with variables, but it's an analogous process. Okay, so if I look at 12, and again, you may have to use the prime factorization ladder or a tree to do this, but I know 12 is 3 times 4 and 4 is 2 times 2. So if I'm looking at the 12 x cubed y, 12 is 2 times 2 times 3, because it's 4 times 3. And then x cubed is 3 x's and a y. Okay, and then 20 is 4 times 5 and 4 is 2 times 2. So 20xy squared is 2 times 2 times 5 times x times y times y. And then finally 16. 16 is 2 to the 4. It's a power of 2. So, and again, but if you can't do that in your head, just take some extra space and prime factorize. 2 times 2 times 2 times 2 times x times y times y. Okay, so if we're looking for the greatest common factor, well, they all have 1, 2. They all have a second 2. They do not all have a 3. So now I'm going to move on to the x's. They all have an x. They do not all have a second x. The second term only has 1x, and they all have a y. So I can underline that as well. Okay, now what does that come out to be? The greatest common factor. 2 times 2 is 4, and then x times y, so 4xy. Okay, that's our greatest common factor. Now, there's an extra piece though, because typically the general rule of thumb is that if your leading term, your first term, is negative, and only if it's negative, we usually factor the negative sign out as well. So we'll factor out like a negative 4xy instead of 4xy. And the reason for that is usually because when we go further, which we're going to look at next week, sometimes once it's factored, it can be factored further. It's easiest to do if the coefficient of the term with the highest degree is positive. And so if it's originally negative, we're going to factor out the negative sign. Okay, so my GCF is negative 4xy. And then my first term should be the original first term divided by the GCF. So you can see here the two negatives cancel. And so now the first term is positive. So negative 12 over negative 4 is 3. X cubed over x is x squared. Y over y is just 1. So that's all that's going to be left from that term. And then in the second term, I've got negative 20 xy squared over negative 4xy. So negative 20 over negative 4 is positive 5. X over x is 1, and y squared over y is y. And then finally, minus 16x squared y squared over negative 4xy. So negative 16 over negative 4 is 4. X squared over x is x, and y squared over y is y. And that is fully factored. Okay, now eventually you want to be able to move away from this first step that we did, just because it takes a really long time. And what you'll notice is the more that you do this, you can actually start to visualize this in your head. So when I'm factoring out a greatest common factor, I look at the coefficients first, or sometimes there's a constant. So between 12, 20, and 16, what's the greatest common factor? It's 4. So that's my the coefficient of my greatest common factor. And then between the x's, I just got interrupted by my son. Hopefully this won't be too long. What's up?
There's someone at the door.
There's someone at the door?
Yeah.
Okay, I better pause this recording. All right, sorry for that interruption. Where was I? I think I was talking about finding the GCF without having to do this expansion, right? So if I think we talked about the numbers already, and now I was talking about the x's. Okay, if I look at the three terms and the x component, in the first one I've got 3, in the second one I have 1, and in the third one I have 2, because it's x cubed, x, and x squared. So between the three of them, they all have 1. We can't say they all have 2 or they all have 3, but we can say they all have 1x. So that's why I could take the 1x out here, okay? And then similarly between y squared, and y squared, they all have 1y. So that's why I can take that guy out as well, okay? All right, I'm gonna let you guys try this one. Oh, I keep doing that. I have to take off the pen before I move up. But I do wanna talk about this last example. And the point that I really want to make about this last example is that before you factor, you should make sure that your polynomial is simplified, okay? Because if it's not simplified, you may actually be missing a greatest common factor or part of the greatest common factor. So if I just look at this long string of terms right now, I can see that they all have an n in them, but between the coefficients, I don't see any greatest common factors. It's not simplified though. So if we simplify it by collecting like terms and look at, okay, here's the n cubed term, here are the n squared terms, and then here are the n terms, okay, I can combine those, right? So negative 7n cubed minus another 1 is negative 8n cubed. And then negative 5n squared minus n squared is minus 6n squared. And then finally 2n minus 12n is minus 10n. Okay, and then if you look between 8, 6, and 10, the greatest common factor is 2. And between n cubed, n squared, and n, they all have at least 1n. So that's my greatest common factor. Knowing that my first term is negative though, I'm going to actually factor out a negative sign as well. Okay, and then negative 8 divided by negative 2 is 4. N cubed over n is n squared. Okay, negative 6 over negative 2 is plus 3. N squared over n is just 1n. And negative 10 divided by negative 2 is 5. And n divided by n is just 1. So this is my factored polynomial. Okay, so I am going to stop this lesson here and we will talk more next time.